The next speaker is Daisuke Ikegami from Shibaura Institute of Technology. And the title of the talk is HOD in L of R and Woodin cardinal in HOD in L of R. Go ahead, please.
Thank you very much. So I think it's 19 years ago when I first met Sakae. And I was an undergraduate student, and I was asking him for advice for graduate school in logic. So since then, he gave me many good advices for my career. So thank you very much, Sakae. Okay, so let me start. Okay, let me start. So let's see. So I would like to talk about determinacy and large cardinal in HOD in a determinacy model. And this is joint work with Nam Trang. So let me start with some background. So first, let me quote some result from determinacy to Skobakis. And Woodin. So they proved two things. So assume AD, then theta is a limit of cardinals with the strong partition property. So here theta is the soup of ordinals where there is a surjective image. It's a surjective image from the reals. Okay. So in the case of GFC model, theta is just a successor of the continuum. But assuming AD, theta is quite large, and it's always a limit cardinal. And it's a limit of large cardinals. So let me say what is partition, strong partition property. So regular uncountable cardinal. Kappa has a strong partition property. If kappa arrows kappa bracket to the kappa mu or any mu less than kappa holds. So let me say, usually I think this part is usually in the GFC world, it's usually at most finite or up to less than omega. But in ADR world, you can get this kind of strong partition property. So let me just remind you what this means. For any partition of kappa to the kappa into new pieces, is a set H of cardinality kappa such that H to the kappa is contained in one of the mu pieces, one piece. So this is the strong partition property. Okay. So theta is the limit of very large cardinals. So that's the consequence of AD. Okay. And actually, from this consequence, they proved the following determinacy results. Assume theta is the limit of cardinals with the strong partition property. Then every suslin and co-suslin set of layers is determined. So they didn't prove AD back from this assumption, but they proved a fair amount of determinacy. So let me remind you of what is suslin and co-suslin. So set of layers A is suslin. If for some ordinal gamma and some tree t on 2 to the 2 times gamma, A is the first projection of the infinite passes of T. Okay. So, right. So this is like a generalization of open set. Sorry, not open set. So it's a projection of closed set. So, okay. So then A is co-suslin. If the complement is suslin. Okay. So using the strong partition property cardinals, they proved that every suslin and co-suslin set of layers is determined. So for example, you can prove that in ZF, every sigma 1 2 set of layers is suslin. So every delta 1 2 set will be suslin and co-suslin. So it's determined. Okay, then, okay, you have delta 1 2 determinacy. Then you can prove that every sigma 1 4 set is suslin. So you get delta 1 4 determinacy. In this way, you can climb up. Actually, you get PD and furthermore. Okay. But they didn't manage to prove AD back from this assumption. Then next result is calculus Woodin. So they went further for the connection between AD and strong partition properties by looking at AD in error bar. The following are equivalent. So actually in error bar, they are equivalent. And actually, the conclusion of the last theorem is also equivalent. Every suslin and co-suslin set of layers determined. So as I said, from 3 you get PD, and if you get PD, you can prove more sets of layers are suslin, and then you get further determinacy. So you keep going in the hierarchy of error bar, then you get the AD in error bar. So that's the scenario. And so in this way, in error bar, one can characterize AT in terms of the large cardinal properties, existence of large cardinals below theta. And after that, Enle, Matthias, and Woodin prove that in general, 2 does not imply 1. So actually, so this equivalence is special for error bar. So if you do some forcing from AD error in error bar, then you can preserve 2, but you kill AD. That's possible. Okay. So by looking at this in error bar, so you can characterize AD in terms of cardinal structure below theta. So the question arises, can one characterize AD in terms of cardinal structure of HOD if phi is equal to error bar. So by the last equivalence theorem, this is possible by looking at the not HOD, but if you look at cardinal structure of error bar, then you can characterize AD. But if you look at HOD in error bar, can you characterize AD? And there has been an extensive study of HOD in error bar. So we have a very fair amount of understanding of HOD in error bar. And let's see. So for example, Woodin proved AD implies theta is Woodin in HOD. And AD gives you a lot of structural properties of HOD in error bar. So what we don't know about the answer to this question, but we asked one test question. So that's the title or abstract of this talk. So does the converse hold, or does in error bar, does AD follow from theta is put in HOD? Okay. So as in the abstract, the answer is no. So I would like to discuss the theorem of this talk. So the theorem is, assume CFC plus delta 1 to indeterminacy. Then there is a model M of CFC such that M satisfies theta is Woodin. Sorry, not M, error bar in M is Woodin in HOD, but AD fails. Okay, so this is the theorem of this talk. So I would like to discuss a sketch of the proof of this theorem. Okay, so the first question is, what is the model M, I think? What is M? And it is, M is L of X of G for Turing cone of X, meaning that there exists some X0, it's a subset of X, and then if you have any X Turing above X0, then that X works for the model. And G would be called omega less than kappa X, generic over L of X, where kappa X is the least inaccessible in L of X. Okay, so this is a model M, and if you look at the error bar in M, then you get the following conclusion. Okay, so let me write some picture first. What's going on here? So okay, so here is kappa X. So this is least inaccessible in L of X. And if you do Levy collapse like this, then it would be omega 1 in L of X of G. Then you look at kappa X plus. So this is in L of X. This will be omega 2 in L of X of G. Okay. Then now we have delta 1 to determinacy in the assumption. So L of X is very small. So actually omega 1 in B is somewhere very high up. Okay. And okay, so actually you can show that this is equal to theta in L of Xg. This is because you do Levy collapse. So L of X of G thinks CH is true. So that's why, as I said, theta is in the model of GFC, theta is a successor of the continuum. So this is true. Okay, and now let's think about L of X. It's a subclass of L of R in L of X of G. And it's a subclass of L of X of G. So actually, using this, you can easily show that this is also theta in L of R. Okay. And also, you can easily show that this is equal to omega 2 in L of R. So L of R in L of Xg thinks theta is equal to omega 2. But as we have seen, theta is a limit of large cardinals in AD world. So AD fails. Okay. So the rest to verify is L of R in L of X of G thinks theta is Woodin in HOD. And this is the same as omega 2 in L of X of G. Okay. And this is the same as kappa X plus in L of X. So that's the situation. Okay. So for the rest of the talk, I would like to focus on this verification. But let's see. So far, any question? Not really. Okay. Let's continue.
Sorry.
Oh, yes.
Yes. So why does theta equals omega 2 imply AD fails?
So as we have seen, if we have AD implies theta is a limit of limit cardinal. It's a limit of strong position cardinals.
Oh, okay.
Yeah. So that's why.
In L of R, right?
Right. Okay. Any other question? Okay, so let's move on. So for this verification, we need some background. So let me go through some background information. So this goes back to Kekuris survey. So assume delta 1, 2 determinacy. Then on the Turing cone of x, L of x satisfies OD determinacy. Here, it's essential that OD means light phase. If you put the real parameters, then that's contradiction. So, yes. So, okay. So, Kekuris survey proved this. And then I think it's, is it, let me see. I think it's, who was it? Kekuris Woodin. And Martin prove that assume now old phase delta 1 to determinacy. Then on the Turing cone of x and y, the theory of L of x and L of y would be the same. So yes, assuming this kind of determinacy, so the theory of L of x for x will be frozen on the Turing cone. Okay. So and in this theory, all the determinacy is inside. Okay. Then Woodin proved that assume delta 1 to determinacy. Then on the Turing cone of x, L of x thinks omega 2 in L of x is Woodin in HOD. Okay, so this series of results show us that the structure L of x, especially hot in L of x on the Turing cone of x, is an interesting structure. So the open question is, what is hot in L of x on the Turing cone of x? So this means that what kind of structure does it have? Is it a fine structural object or not, and so on. And we still don't know the answer to this, but Woodin has some partial answer or close to this question. So assume delta 1 to volte-face determinacy. And on the Turing cone of X, for G for omega less than kappa X, generic over L of X. So kappa X is here. Kappa X is the least inaccessible in L of X. Hot in L of X of G. So instead of hot in L of X, you do collapse, and then you look at hot in L of X of G is of the form L of M infinity of lambda, where M infinity is the direct limit of countable iterate of M1. So M1 is a canonical model in a model, fine structure in a model with one Woodin cardinal. And you look at the countable iterates of M1, then that forms a directed system. And then you take the direct limit, and that's M infinity. And lambda is partial information of iteration strategy of M infinity. Okay. So hot in L of X of G does not know how to iterate M infinity or M1 fully, but it knows a certain amount. It can iterate M infinity or M1. Okay. So then, moreover, so Azaf, just a moment. What? Just a moment. Right. I think so. I cannot. Sorry, I cannot open chat now. Can you hear me? Okay, just to see that I'm okay. So actually, we don't know. So what we know is hot in L of X of G is a subclass of hot in L of X by homogeneity of the forcing, but we don't know if they are the same. Okay. So we don't know if hot in L of X of G includes hot in L of X. That's the question, I think. Okay. So, okay, good. So let's see. So actually, hot in L of X of G is a high structural object, and it satisfies GCH, and then so as I said, M1 is in a model with a Woodin cardinal, and since M infinity is a direct limit, so it also has a Woodin cardinal. Then letting delta infinity be the Woodin cardinal in M infinity would improve that B delta infinity in M infinity is the same as B delta infinity of hot in L of X of G. So hot in L of X of G is bigger than M infinity, but they agree with M infinity up to delta infinity, which is Woodin cardinal in M infinity. And also hot in L of X of G satisfies that delta infinity is Woodin. And delta infinity is actually the same as omega 2 in L of x of g and theta in L of x of g. Okay. Okay, so now, okay, so this is the result by Woodin. Okay, so now you can imagine why we use this M. Okay, so back to M, which is L of x of g. Then we knew that, let me write, kappa x is equal to omega 1 in L of x of g. Then kappa x plus L of x is equal to omega 2 in L of x of g. And this was the same as theta in L of r in M. Okay, so what we want is M thinks, sorry, L of r in L of xg is theta is Woodin in HOD. But from the Woodin's result, what we have is L of x of g thinks theta is Woodin in HOD. So there's a subtle difference. So we need to compare HOD in L of x of g, which we already know what kind of structure is, and HOD in L of r in x of g. So that's the difference. Okay, so the question, obvious question is HOD in L of r of L of x of g is the same as HOD in L of x of g. So if we could prove this, we are done. But actually, we don't know if this is true. Actually, last night I got some idea to prove this, but it's too dangerous to say, yeah, we can prove this. So instead of trying to prove this, let me prove something without using this conclusion. Okay, but anyway, what we want is this. So L of r in L of x of g thinks theta is Woodin in HOD. Okay, and in this case, let me note that theta is the same as delta infinity as we discussed. Okay. Okay. So what shall we do? So what we know is easy consequence is, so we don't know if they are the same, but we know that one inclusion so HOD in L of r in L of x of g is a subclass of HOD in L of x of g because L of r in L of x of g can be easily defined in L of x of g. So it's OD in L of x of g. So HOD in L of r in L of x of g is included in HOD in L of x of g. Okay. But we don't know if the inverse inclusion is true. But now all we need is actually, so we don't know if two models are the same, but all we need is if they agree up to delta infinity. Sorry, I should put out here. messy notation. Okay, so this is all we need. Why? Because we want to verify that HOD in error var in error x of g thinks delta infinity is Woodin in HOD. Sorry, error var in error x of g thinks theta is Woodin in HOD. And we already know that, so this model, error x of g already thinks delta is Woodin in HOD. And this model is included, okay? And so if delta infinity is Woodin is a pi 1 property of B delta infinity, B delta plus 1. Okay, so if we had this, and then a smaller model also thinks delta infinity is Woodin in HOD. Okay. Okay, so this is all we need. And so then to prove this, first question would be, how do we recover HOD in error x of g in error var in error x of g in an OD fashion? Okay, and the basic point is, well, error x of g, error var in error x of g is a Solovay model over error x. So using this, so you want to recover from a Solovay model its original generic extension L of x of g. So that's what we want to do. And this is already studied well. How to recover generic extension L of x of g from, not fully, but in some way in the theory of L of x of g using only Solovay model. Okay, so here is the lemma by Woodin. So this is a general lemma, but let me put it in the way in this context. So with the above notations, let P sub x would be small g in error var in error x of g, such that for some alpha less than kappa x, g is O omega less than alpha generic over L of x. So please note that here we use parameter x. Okay, so this becomes the essential point later. Then, okay, so this is a poset. So the poset says, okay, so this is a collection of small generic over L of x inside L of r in L of x of g. And then what would happen if you force visit over L of r in L of x of g? So let's see, let H be P sub x generic over L of r in L of x of g. And let G prime be the union of H, meaning that so H is a filter, so it's a collection of coherent small generics. And then if you take the union, then what you could expect is you get the Levy collapse generic. So G prime is actually called omega less than kappa x generic over L of x. And reverse inclusion, yes, correct, yes. So you just extend, if you stronger conditions extend the smaller condition. Okay, so then you can recover the reals of L of x of g inside L of x of g prime. So they have the same error bar. Okay, and using the homogeneity of col omega less than kappa x, so this is enough to recover the theory of L of x of g using L of x of g prime. And moreover, the P sub x is weakly homogeneous, actually homogeneous. Homogeneous in L bar in L of x of g. Okay, so this is a homogeneous forcing in L bar in L of x of g. So using this and the above fact, you can compute the theory of L of x of g, or the OD HOD in L of x of g inside L bar in L of x of g. Okay, but the problem is here you're using x as a parameter, so that's a problem. So the problem is px needs x for parameter. So actually what you can say is HOT in L of x of g is a subclass of HOT sub x in L bar in L of x of g. Okay, and but x cannot be in HOT in L bar of L of x of g. Even x cannot be HOT in L of x of g. So using x as a parameter is too strong in this context. Okay, so how should we fix this problem? And the point is, the above lemma holds with P sub y and L of y for any y above x in L of r of L of x of g. So if you take any y above x inside L of r in L of x of g, then you can prove this lemma replacing x with y. So you can say to recover HOT in L of x of g, you can say, okay, so for a Turing cone of x, for a Turing cone of y, you do this forcing py and you work so small generics over L of y, then you force with it over L of r in L of x of g, then you can recover the HOT in L of x of g. Okay, so that, and this gives you HOT in L of x of g is OD inside L of r in L of x of g. So we don't know, maybe it's true, but if HOT in L of x of g is a subclass of HOT in L of r in L of x of g, but certainly HOT in L of x of g is definable in L of r in L of x of g. Okay. So using this, actually, okay, so because that what we wanted is it was, let's see, just a moment. V delta infinity in HOT in L of r in L of x of g is the same as V delta infinity hot in L of x of g. So this is all we wanted. Okay, so we are getting close. Then we also knew that, let's see, from Woodin's results, L of x, m infinity, b delta infinity is equal to b delta infinity in hot in L of x of g. And m1, m infinity. So m infinity was the iterate of m1. Okay, so that's the situation. Okay. Now we use another fact by Steele. So Steele proved that actually V delta in M1 thinks V is equal to hot. So M1 is a canonical inner model. So using the extender sequence of M1, you can easily prove that it's OD via sequence, using the sequence as a parameter or predicate. But here, what's non-trivial is you don't use sequence. And you can claim that the sequence is ordinally definable inside M1 as a structure in the language of set theory. So using this, what we know is now, so we have this fact and this fact. Okay. So, and we now know that hot in L of x of g is OD inside L of R in L of x of g. So in particular, V delta in M1, sorry, just a moment. And we have this elementary embedding. So M infinity. So this also thinks V is equal to hot. Okay. So using this fact, two facts, and the last fact, you can conclude that actually, so B delta infinity in M infinity is a OD inside hot in L of x of g. Sorry, L of R in L of x of g. So actually, B delta infinity, M infinity, which is the same as B delta infinity hot in L of x of g, is a subclass of L of R in L of x of g. Sorry, hot in L of R. Okay. So what we wanted was B delta infinity in hot in L of x of g is the same as B delta infinity in hot in L of R in L of x of g. And this is true because of this inclusion. Okay. And from this, we can conclude that L of R in L of x of g is since theta, which is equal to delta infinity, is Woodin in hot. Okay. So this is what we wanted. So this is the end of the proof. Okay. So that, okay, so that's the proof. So let me just discuss some questions before ending the talks. So the first question is hot in L of R in L of x of g the same as hot in L of x of g? Maybe it's easy to prove this, but we just didn't know. Okay. And then the second question is, there are many canonical models such as this kind of things, and we don't know its HOD well. So actually, another possible example of the theorem is the following kind of structure. What is HOD in L in M1G, where G is called omega less than delta, generic over M1, and delta is a Woodin cardinal. In M1. Okay, so this kind of basic structure, we don't know what kind of structure it is. And it could be similar, this kind of hot in L of R in M1G, could be similar to hot in L of R in L of X of G. Then maybe theta is Woodin, and then of course the AD fails in this structure. Okay. So that could be another example. Okay, so I will stop here. Thank you very much.
Okay, thank you very much. Do you have any questions, comments? Okay, Erin, go ahead. Erin. Oh, it's just clap, right? Sorry.
Well, that was very interesting talk. That was very nice.
Ah, thank you. Yeah, glad to hear that.
Hiroshi?
Thank you very much for nice talk. And I don't know much about this topic, but so my question is, so your research is based on the Woodin's theorem, saying that AD implies theta is Woodin cardinal in HOD, right?
Uh-huh.
So can you prove more? I mean, so for example, can you prove that AD implies theta is some, so for example, can you prove that AD implies there is a Woodin cardinal below theta in HOD or something like this?
No, I think in case of error bar, theta is the only Woodin cardinal in HOD.
I see.
But what you can prove is there is a definition of a thoroughbase sequence.
Yeah.
Theta 0, theta 1, theta 2. So if alpha is a successor ordinal, then theta alpha is always Woodin cardinal in HOD.
I see.
But in error bar, theta is equal to theta 0.
I see.
That's why there's only one Woodin cardinal in HOD.
I see. So do you have any candidate to characterize it?
Right, there are many large cardinals. Basically, for example, in hot in error bar, every regular cardinal in error bar is measurable. And there's a lot of such property. So we can try other things, but I have no idea whether we can characterize AD from that.
I see. Thank you very much.
Okay, so now, Erin, you have a question, right?
Sorry, now I do have a question, I guess. Well, what if V equals HOD is your question?
So in error bar, you mean?
I guess I don't.
Okay, so in error bar, if AD holds, then the axiom of choice fails, right?
Okay.
But in HOD, axiom of choice is always true. So in error bar, if you assume AD, then V cannot be equal to HOD.
Okay. And in general, I saw that like AD is equiconsistent with infinitely many Woodin cardinals. I mean, this is just like a general fact, right?
Right.
But that doesn't mean that like Woodin cardinals are inconsistent with AC or anything, right?
No.
Okay.
There is a model of, for example, M1 has a Woodin cardinal, and the M1 is a model of GFC.
Okay.
And the M1 thinks B is equal to HOD.
Okay, but Elevar it is not.
Elevar is not.
Yeah. Okay.
So Sakae?
Okay. So connecting to the question of Hiroshi, is it so that the Woodin cardinal is the largest possible large cardinal in HOD, or I mean, can you think of some larger cardinals in HOD in this context?
That's a very good question. Actually, we don't know. So there is some wild conjecture from inner model theorists. Like if you look at HOT in a very strong determinacy model, then you cut it at theta, then in B theta there is a super compact. But so, this is really wild conjecture.
Wild, you can even consider super compact, right? So
right.
Yeah. So assume that this is okay. Then how about the implication of HOD, supercompact in HOD implies AD holes in LR or something like that?
It would be great. Let's see. I don't know about the candidate of the supercompact in this case, because theta is a limit of large cardinals. Woodin cardinal is really not really like a large cardinal. It can be measurable, but in this case, it's not measurable in LR. So it's like Woodin cardinal is a limit of large cardinal properties from LR. So where is super compact?
Kind of structure in case of super compact, right?
Right. So we don't know what is the cardinal in HOT in determinacy model. We don't have a clear picture of it. So this is really a wild conjecture.
Okay. Thank you.
Andres?
Yes, thank you. So first of all, very nice talk.
Thank you.
And so do we know how to characterize the sequence of Woodins that we identify? I mean, here we have the smallest one is the HOD of theta. Is the theta of HOD. Can we say something about the others in a definable manner?
So I think the conjecture is in AD plus V0 facet of the real, then all the Woodin cardinals in HOT, the theta alpha plus 1.
Yes, but in LFR.
In LFR, I think, let's see, in LFR, HOT in LFR, I think theta is the only Woodin cardinal.
In some inner model of choice? No, I'm saying, you know from LFR how satisfying determinacy, you can find a sequence of Woodin cardinals that in some model...
I see what you mean. Yeah. Okay. I don't know. So, but you want a model where there's no Woodin cardinal in HOT?
No.
Okay, I'm not sure.
Yeah,
I'm not sure what your question is.
Yeah. So okay, so you know from LFR satisfying determinacy, somewhere in some extension, you're going to find a sequence of Woodin cardinals. That when you do the
Woodin cardinals in which model?
In some model. In some extension of LFR, you're going to find a sequence, an omega sequence of Woodin cardinals, that when you collapse, you recover LFR, right? That's the derived model theory.
Right.
So the first Woodin of that sequence is the theta of HOD, is the Woodin of HOD.
I'm not sure because. For example, if you try to get omega Woodins from HOT in LFR, using, then basically you do a pre-reinforcing, right?
Yeah. But
Yes.
so you cannot identify the sequence, but you should be able to identify each one.
I'm not sure because let's say this pre-reinforcing. So basically, all we know is the soup of omega many Woodin cardinals is omega 1 in L bar. So I don't know if how to identify the first Woodin cardinal in that model. Basically, you stack a chunk of information of omega many times using pre-reinforcing, and then it may depend on conditions in pre-reinforcing over L bar, right?
All right. Thank you.
Okay. So, any other questions? Comments? Okay, so can speak again.
Thank you.